everyone, this is Miss Lloyd again, and we are looking at logarithms today. So logarithms are the inverse of our exponential functions. So just like our multiplication and division are inverses, addition and subtraction are inverses, our exponential and logarithmic functions are inverses of each other. And so we can see this a little bit when we go back and forth from logarithmic to exponential form. So if I want to get rid of my base so that my exponent becomes, something that's not an exponent, typically if we're trying to get rid of an exponent itself, we would take a type of root. So if it was a square, we take a square root. If it was a cube, we take a cube root. If it was to the fourth power, we take a fourth root. But unfortunately, we can't take an x root. That's not really how it works. We can only take roots that we know. So because I can't get rid of the exponent, I'm going to get rid of the base. And we do this by taking the log of the base on each side. So again, my base is this b and the x is its exponent. So when I do the log of the base on both sides, the log base b and the base b cancel each other out because they are inverses of each other, leaving us with just an x. And then on the other side, because what we do to one side, we have to do to both, we end up with a log base b of a. So we can go the other way as well. Say I have my x is equal to log base b of a, and I want to get rid of the log. Then I would do a base of b to both sides. The log base b and the big base b cancel each other out because they're inverses, the same way as a plus 2 minus 2 would cancel each other out, or a 2 times and then a divided by 2 would cancel each other out. It works the same way. And so because the log and the base have now canceled out, I'm just left with the a. And because I've done a base on the other side, then whatever that x is has now become the exponent. So we can go back and forth just like that. So here, my base is a 3. And so they want me to put this into exponential form, which means that they want me to get rid of the log. So because I have a log base 3, then that means I'm going to do a base of 3 on both sides. So my log base 3 and my big base 3, they cancel out. I'm left with an 81 on the left side. And then because the 3 is now the base, that 4 becomes the exponent. So 3 to the fourth power. And when we switch forms like this, it will make it a little bit easier to see. We have 3 to the fourth power is equal to 81. So basically what this is saying when we do a logarithmic function is we're asking, okay, to what exponent do we put 3 in order to get 81? And the answer is 4. So the log is undoing that exponential, that exponent process. So we're asking what base, or to what exponent do you put 3 in order to get 81? That's our 4. So this next one, we're in exponential form because we can see the exponent there, and they want us to change to log. So because my base here is the 5 has the exponent, I'm going to do a log base 5 on both sides. My log base 5 and my big base 5 are going to cancel out, leaving the 3 alone on the left side. And there's nothing that's going to cancel out on the other side, so we'll have a log base 5 of 125. So again, it's basically asking to what exponent do we put 5 to in order to get 125, and that answer is 3. This next bit, we are going to evaluate each logarithm at the given value of x. So this basically means that they want me to plug my 1 in for the x value here. So what we're asking ourselves now is to what exponent do we put 6 in order to get 1? So 6 to the first power would give us 6, 6 squared would give us 36. So at what point do I have an exponent that I give 6 in order to make it 1? And that's when we remember about one of our special exponents. If I have anything, just about anything, to the power of 0, we're going to end up getting 1, as long as it's not 0 to the 0 power. So 6 to the 0 power would end up getting us 1. This is where exponential rules, or exponent rules, come into play. So that leads us to some of the properties of our logarithms. So because just about anything to the 0 power is 1, then anytime I have a log to some base of 1, my solution is always going to be 0. We also have a situation where, okay, I'm asking myself, to what base do I have, or to what exponent do I have a in order to get a? That would mean that I would have a to the first power. A to the first power would remain itself. Our next situation, We have a log with the base of a, and it has the same number inside of the log as the base. So that base and the log with the same base would cancel each other out, leaving you with just the x. So it's just showing that inverse property. We also have our one-to-one property. So if we have a log of x, log base a of x, and a log base a of y, because those log bases are the same, that means that the numbers inside are also the same. This is very similar to when we had exponents or bases that were equal, which meant that our exponents had to also be equal. So this is our one-to-one property. And we can use these to simplify our problems here. So to simplify our logarithms. Sometimes when I do these, I like to think of it a little bit differently. Instead of just memorizing a bunch of properties, I already know all the properties for exponents, so I like to kind of turn these into those. So anytime we're simplifying, I personally like to set these equal to x. I'm not as familiar with my logarithms, or at least I know my students aren't going to be very familiar with their logarithms quite yet because they haven't worked with them. So I'm going to get rid of the log. It has a base of 9, so I'm going to put everything to a base of 9. My log base 9 and my big base 9 are going to cancel out, leaving me with 9 is equal to 9 to the power of x. So this here, we can see that property working out because if my bases are the same, I've turned it into a one-to-one. That means my exponents have to also be the same. So we can think of it as my log base 9 and my big base 9 canceled out, leaving me with just 1. They're inverses of each other. It'd be the same as if we had 2 divided by a 2. We can also use this understanding for when we're solving. So because I have a log base 5 equal to a log base 5, that means that things inside have to be equal to each other. Say we don't remember that though. There's another way we can look at it. I can think of it as I'm not a big fan of working with logarithms, so I'm going to get rid of them by putting everything to the base of 5. When I do that, the big base 5 and my log base 5 cancel each other out, leaving me with just x squared plus 3 equal to the 12th. And then we can solve from here. Next thing we're going to do is look at graphing these. So when I graph, I have to keep in mind, or I like to keep in mind, that my 3 to the power of x and the log base 3 of x are inverses of each other. Something great about inverses is that, okay, I know how to graph a 3 to the x. I can use this t-chart every time. And because these two are inverses, that means that their t-charts are also going to be inverses. So if I were to take my calculator, and if your calculator has a function to where you can use a log base of 3, most calculators have something that's just a log. Anytime we see a log by itself and it doesn't have any number for the base, this is a base of 10. This is called our common base for our logarithms. So if you have something where you can plug in a 3 for your base of your log, you can plug in 1/9, 1/3, 1, 3, and 9. And your y values will all end up being -2, -1, 0, 1, and 2. So because they are inverses of each other, that means our x and y values are inverses. They switch, they trade places. So when I graph these, I'll graph my exponent first. And then I can graph the logarithmic, so using that t-chart. We can see that they reflect over the y is equal to x line. We can also see that as I keep plugging in smaller and smaller fractions, we're going to get closer and closer to where x is equal to 0, and we're not actually going to cross it. So this is kind of a fun fact about our logarithms. We can't plug in anything that is negative. So when I'm doing my graphs, I like to find the t-chart for the exponential function first. It's a little bit easier to plug into my calculator. And then I just switch those x and y values of the chart and plot those new points. I'm going to kind of go over this next bit a little bit with my students, so I'm going to skip down. So here it looks like we're going to have a little bit of shifting because I have a -1 here and it's not inside of the log. With my x value, that means it's affecting my y. So this is going to cause my function to move down one space. It's the same as if I subtracted 1 from all my y values. So in order to do that, I need to figure out what my t-chart is going to look like. Because this is a base of 3, I'm going to first find the t-chart for my 3 to the x power. And then I'm going to switch my x and y values in order to get just my log base 3 of x, since those are inverses of each other. So now that I know that this is the t-chart to my parent function, if you will, I'm going to move everything down by subtracting 1 from all of my y values. And so from here, I'm just going to plot those new values. And there we have it. So next bit is just about our natural logarithms. So this is when we have a base of e, which is our natural base. So basically we use this ln as an alternative to saying log base e, log base e, log base e. I like to think of it as, I know we call it in English natural log, but in most other languages you would call it log natural or log natural if you want to sound fancy. I don't sound fancy, I just sound like me. So we use this ln in order to represent the log base e. Writing out log base e over and over and over again can get really, really tiring for those who use it all the time. So they decided, mathematicians, we like to work smarter instead of harder, so we're just going to use ln instead. But we do want to keep in mind that this is a log base of e. It's going to help us with our solving a little bit later down the road. And all the properties that we had for the logarithms are exactly the same for our natural bases and our natural logarithms. So if we have a natural log of 1, the solution is going to be 0 because we're asking ourselves to what exponent do we put e to in order to get 1. And because e is not equal to 0, it's equal to 2.7, and then that kind of just goes on forever, kind of like pi. Then we know that if we put it to the 0 power, it's going to be equal to 1. Same thing, if we put e to the first power, it's going to be equal to itself. And because this is a log base of e and a big base of e, the e's would cancel out, leaving the x to come down on its own. And it also obeys the one-to-one function, to where if we have a natural log of one number equal to natural log of another number, then those numbers have to be equal to each other. If we have the same base, then the insides have to be the same as well. And so here we can just practice the log function in our calculator. So some of us have an ln button in our calculator, and some you have an e button, but you have to kind of shift maybe above it will be your ln. So when I go into my calculator and I plug in ln of 0.01, and you can always pause if you like and figure it out in your own calculator and see if we get the same thing. When I plug it into mine, and this is one that I've used on my phone as well, so your phones also have these functions, you get negative 4.6052. And that number does go on, it doesn't stop there. I just like to round to 4 numbers after the decimal point because all I'm doing is plugging things in, so why not go for it? The next bit, we're going to use the properties of natural logs to simplify each of these expressions. So again, I do like to use the properties themselves, but I also like to think of it as, okay, even if I don't memorize the properties, I can think of it with the inverses, so work it out kind of like an algebra problem. So I could take both of these because this is a natural log. This is like a log base e. Those are the exact same things. So we could see here that we have an e and an e, so a log base e and a big base e. Together, those are inverses, they'll cancel each other out, and so we would end up with 1/3 is equal to x. So I tend to not go back and forth from ln to the log base of e, but I feel like if we have the log base e, it's a lot easier to see the canceling out process. Next, we're just going to change forms. So again, this ln is a log base e. So if I want it in exponential form, that means I'm trying to get rid of the log. In order to get rid of a log base e, I'm going to take both sides to the base of e. The log base e and the big base e will cancel each other out, leaving me with 2 is equal to, nothing's canceled out on this side, so I now have e to the 0.69. And if we were to plug that into our calculators, e to the 0.69, we're going to get very, 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 very close to 2. It's not going to be exact because that 0.69 is something that was rounded. Next, we're going to change this into logarithmic form. Before I do that, I want to get rid of the radical here. And by getting rid of it, I'm not going to take the other side to the 6th power. I'm going to rewrite this in my exponent form. This is something that my students and I haven't done for a little while. It's been at least an entire chapter, if not more. But remember, anytime we have a radical, it's like having the exponent divided by that radical. So I now have e to the 4 over 6. So now I want to get rid of our e. I would rather have the log instead. So in order to get rid of the base of e, I'm going to take this to the log base e. Because I have a log base e and a big base e, those two are going to cancel out. I'm also going to reduce this 4 over 6 because that gets on my nerves if it's not reduced. And so this is a 2 over 3. And I now have log base e of 1.95. And again, we don't really write log base e, we use a natural log. So my final answer is just going to be cleaning that up a little bit. And this is our logarithmic form. And so this is as far as I'm going to take you guys. I'm going to do a few more examples with my students. I hope you found this helpful. If you did, please feel free to like and subscribe. And if you think that there's maybe one of your friends that's struggling a little bit with logarithms and this could help them out, please, please, please feel free to share it. Spread the love.